Okay, physics class. We're going to go ahead and do a couple of days on sound waves. So last week we covered waves in general, how generally waves work. Monday and Tuesday of this week we talked about light waves. The next 2 days we're going to talk about sound waves. I'll have a project that I'll perform for you. Unfortunately, I wanted you to do this project in class tomorrow. The project I'm going to do tomorrow, I wanted you to do in class, but that won't be possible. So I'll demonstrate it for you and show you how you can do it yourself if you want to. Today I'm just going to talk about how sound waves, in extreme sound waves work, which is when you can go actually faster than the speed of sound and what effect that has. Sound waves, if you remember, are longitudinal compression waves. So when something makes a sound, it squeezes and releases the air molecules next to it. And that squeezes and releases the air molecules next to that and next to that until the sound wave reaches the air molecules inside of your ear and it squeezes and releases them. And that causes your eardrum to wiggle, which sends the sensation of sound to your brain. Now, this is air compression. An extreme form of air compression is a bomb. When a bomb blows apart, say, a building, it's not the metal or the fire in the bomb that does it. Surprisingly, it's the shock wave of the air. It's actually air molecules that are breaking that building apart. It seems hard to believe that that would do that, but it does. When you can compress the air molecules down tight enough, then they become almost like a solid that's pushing through those walls. We're going to talk about something a little less extreme than that, and that is sonic booms. And these are explosions the sound of an explosion that happens when, say, an airplane goes faster than the speed of sound. We used to hear these all the time in San Diego. The Navy jets would fly supersonic above the speed of sound, and it would actually cause an explosion sound. Everybody knew what it was. They weren't concerned about it, but it would actually rattle the windows in your house. And finally, they passed a law or the Navy set a policy that they couldn't do that anymore over a city. So now if they're going to fly supersonic, they have to do it over the desert or over the ocean somewhere. So we'll watch about a 5-minute video on how sonic booms work and supersonic flight works, and then I'll show you a brief example from a YouTube of an actual sonic boom.
Humans have been fascinated with speed for ages. The history of human progress is one of ever-increasing velocity, and one of the most important achievements in this historical race was the breaking of the sound barrier. Not long after the first successful airplane flights, pilots were eager to push their planes to go faster and faster. But as they did so, increased turbulence and large forces on the plane prevented them from accelerating further. Some tried to circumvent the problem through risky dives, often with tragic results. Finally, in 1947, design improvements such as a movable horizontal stabilizer, the all-moving tail, allowed an American military pilot named Chuck Yeager to fly the Bell X-1 aircraft at 1,127 kilometers per hour, becoming the first person to break the sound barrier and travel faster than the speed of sound. The Bell X-1 was the first of many supersonic aircraft to follow, with later designs reaching speeds over Mach 3. Aircraft traveling at supersonic speed create a shockwave with a thunder-like noise known as a sonic boom, which can cause distress to people and animals below, or even damage buildings. For this reason, scientists around the world have been looking at sonic booms, trying to predict their path in the atmosphere, where they will land, and how loud they will be. To better understand how scientists study sonic booms, let's start with some basics of sound. Imagine throwing a small stone in a still pond. What do you see? The stone causes waves to travel in the water at the same speed in every direction. These circles that keep growing in radius are called wave fronts. Similarly, even though we cannot see it, a stationary sound source, like a home stereo, creates sound waves traveling outward. The speed of the waves depends on factors like the altitude and temperature of the air they move through. At sea level, sound travels at about 1,225 kilometers per hour. But instead of circles on a two-dimensional surface, the wave fronts are now concentric spheres, with the sound traveling along rays perpendicular to these waves. Now imagine a moving sound source, such as a train whistle. As the source keeps moving in a certain direction, the successive waves in front of it will become bunched closer together. This greater wave frequency is the cause of the famous Doppler effect, where approaching objects sound higher pitched. But as long as the source is moving slower than the sound waves themselves, they will remain nested within each other. It's when an object goes supersonic, moving faster than the sound it makes, that the picture changes dramatically. As it overtakes sound waves it has emitted, while generating new ones from its current position, the waves are forced together, forming a Mach cone. No sound is heard as it approaches an observer, because the object is traveling faster than the sound it produces. Only after the object has passed will the observer hear the sonic boom. Where the Mach cone meets the ground, it forms a hyperbola, leaving a trail known as the boom carpet as it travels forward. This makes it possible to determine the area affected by a sonic boom. What about figuring out how strong a sonic boom will be? This involves solving the famous Navier-Stokes equations to find the variation of pressure in the air due to the supersonic aircraft flying through it. This results in the pressure signature known as the N wave. What does this shape mean? Well, the sonic boom occurs when there is a sudden change in pressure, and the N wave involves two booms, one for the initial pressure rise at the aircraft's nose, and another for when the tail passes and the pressure suddenly returns to normal. This causes a double boom, but it is usually heard as a single boom by human ears. In practice, computer models using these principles can often predict the location and intensity of sonic booms for given atmospheric conditions and flight trajectories, and there is ongoing research to mitigate their effects. In the meantime, supersonic flight over land remains prohibited. So are sonic booms a recent creation? Not exactly. While we try to find ways to silence them, a few other animals have been using sonic booms to their advantage. The gigantic Diplodocus may have been capable of cracking its tail faster than sound, at over 1,200 kilometers per hour, possibly to deter predators. Some types of shrimp can also create a similar shock wave underwater, stunning or even killing prey at a distance with just a snap of their oversized claw. So while we humans have made great progress in our relentless pursuit of speed, it turns out that nature was there first.
All right, so I'll have a few questions for you to answer on that video on the assignment sheet, and they're all very straightforward questions. So go ahead and do that. I'm going to give you one more quick video of an actual sonic boom from a Navy jet. And if you go on YouTube, you can find a number of examples of these, but this will be a brief example.
Sonic booms caught on video.
Okay, so that gave you a couple of examples of a sonic boom. So go ahead and fill out the assignment. This is the assignment for Wednesday, May 20th. It's due on Tuesday, May the 26th. You do have some not accepted after assignments coming up on May the 26th. I would actually give those priority. Those would be all the extra credit assignments that came before April the 27th. I'll still accept those for full credit. They're extra credit, and get as many points as you can any way you can. And then the April 27th which is the April 27th and May 4th, those 2 weeks that begin with those dates are due on May the 26th. So you got some assignments coming up. I would give those priority and then catch up if you need to catch up. Anyway, I hope to hear from you sometime if you need any help. And please feel free to call me 7 days a week or email me 7 days a week, and I'd be happy to help.